Mega of the school. Okay. Arkis Kainitis told you about the Riga dynamo experiment. It ran first time successfully at November 11, 1999, right? And only 2 weeks later was the first successful run of the Karlsruhe dynamo experiment. The Karlsruhe, or the heart of the Karlsruhe dynamo, is a vessel in which, through which sodium, liquid sodium, is pumped by 3 pumps, and a complicated system of channels makes a helical flow, so that it was expected and it was confirmed that in this arrangement self-excitation of a magnetic field takes place. You see here the dimension of this device: radius less than 1 meter, height less than 1 meter. We have in this vessel 52 identical structures called spin generators. There's a central channel through which sodium flows, and it is surrounded by a helical channel. The typical lengths are A, 21 centimeters, and the pitch of this screw 19 centimeters. Okay, this you see here the connections between the central channels, for example, and all the central channels are in one loop, central loop, and pumps of up to 210 kilowatt are available, one for this central loop, and there are 2 loops for the helical channels, so that you can also do the, or make this device unsymmetric. The motivation for this experiment, in the Riga case, it was simply to take the device where the lowest dynamo threshold was expected. That's why the Ponomarenko dynamo was taken. Here, the idea in the background was the convection in the Earth's core, and this Karlsruhe device contains just these convection rolls here, but they fill here all the volume. The experiment was proposed by Busse in 1975. The Earth was one motivation. There was another favorable circumstance. In the Karlsruhe Research Center were investigations for sodium loops for fast breeder reactors. And at the beginning of the 90s, the official opinion about fast breeder reactors changed, and the research was stopped. And then equipment for sodium experiments was available. It was just used for this experiment. Okay, it is a pleasure for me to mention that this experiment proposed by Busse is in fact also a Riga dynamo. In 1 year after the paper where the alpha effect was first time calculated, Arkis published a paper where he thought about a flow pattern in the Earth's core, and he has shown that such an arrangement should be possible to make a a dynamo. In the context of the Karlsruhe dynamo experiment, the flow pattern used, sorry, the flow pattern used by robots, it is not Paul robots but Glynn robots, played a big role. I will come back to. You see, it is just the flow, similar to the flow, which is organized in the dynamo module in Karlsruhe. Again, this is the dynamo model, and here I show you a few pictures from the time when it was under construction. You see here the spin generators, you see the flows connecting, or the channels which connect the helical channels of these spin generators. Okay, then the cover was made on this, and here it is already covered. You see the tubes for the connecting flows between the spin generators, and then all this was put in a vessel in a, I think not argon but nitrogen atmosphere in Karlsruhe, and yeah. Oh, sorry, that was nonsense. Yeah. And you see here again this container with a dynamo module and all the surrounding sodium tank, pumps, cooling system in a building of about 11 times 11 times 10 meter, a rather large device. Okay. There were two branches in the theory of the experiment. On one side, numerical simulations done by Busse and Tilgner, and there's a series of papers in the years 96 to 2004. And on the other side, investigations made in the framework of mean field electrodynamics in the group in Potsdam, and also later, I think it was 2003, Axel was included in the calculations. The results of both approaches are in good agreement, in some sense complementary to each other, and I will only speak about the mean field approach. Again, the robots dynamo. Robots considered flows like this. It's only an example. You had also other flows which can be represented in a simple way by sine and cosine x and y. This is a spatially periodic flow, periodic in x and y, and independent of the third coordinate set. Perhaps you remember what I said about Cowling's theorem, or the planar form of Cowling's, planar version of Cowling's theorem. Such a set-independent flow pattern can act as a dynamo only in combination with a set-dependent magnetic field. If you cancel the set dependence here, then it is a situation where you cannot have a dynamo. Okay, but you can have such solutions, and the conditions under which they don't decay are given here. Define Reynolds numbers for the flows in the xy plane and for the flows in z direction, and then the condition for the existence of non-decaying modes is this. K is again this edge of the cross-section of the spin, or later spin generators. Here plus half of the period interval. And K, or 1 over K, is the wavelength in that direction. Okay. I wrote a function phi, and I say it simply. It behaves like this. It is equal to 1 for small Rm perpendicular, and it decays then later. And here is the product. This product. Okay. The most easily excitable modes have a part which is independent on x and y, part which is a homogeneous field in the xy plane, and the existence of this homogeneous part gives rise to make a mean field theory. So start again with the induction equation. Define mean fields simply by averaging over such surfaces. I think I have it also here. Such surface that you can shift it. Okay, put B equal to B bar plus, say, fluctuations, and U equal to U bar and fluctuations. Assume that you have no mean motion. And we do not consider only this flow pattern, but also others which are closer to the experiment. And we assume in all cases that U is periodic in X and Y. And that it changes sign if you shift the pattern by A in this direction or in this direction, and this steady. So another flow pattern which we will consider later is closer to the experiment. You have here the central channels with the up and down flow, and here's the healing lip channels where you have this rotation and in addition an up or down flow. Okay. You can take the average of the induction equation, mean field induction equation, and make again the assumption that the electromotive force can be represented in this way, a part which proportional to the mean magnetic field without derivatives, and one with spatial, with first order spatial derivatives. Ignore all higher contributions. The Aij and Bijk must be independent on x and y. This is just the definition of our mean. And yeah, you should go a bit back. If you turn the pattern by 90 degrees about, for example, this axis, it doesn't change and by 90 degrees. Or you can, of course, also take this axis, then it changes, but if you then again shift it in x or in y direction, you can make that it coincides with the original pattern. In my, I think, second lecture, I explained that tensors which are invariant under rotations about an axis are axisymmetric vectors, and I explained to you how you can construct them. It is a simple exercise to show that the possibility to rotate a pattern by 90 degrees leads to the same result as I said for continuous rotation. You come to this structure of E and B, and okay, and you can write down for the electromotive force this general relation with 9 coefficients. 3 with B, 3 with curl of B, and 3 with the gradient, the symmetric part of the gradient tensor of B. But you can reduce this. If this is just repeated from the slide before, if U is independent of Z, then you can first conclude that 4 of these coefficients are equal to 0. In the pattern, plus Z and minus Z is, you cannot distinguish it. If you go in X or Y by A further, then you have again this old situation. So you cannot, if you are alone in this pattern, you cannot decide where is north or south. Mm-hmm. And that is why you cannot have terms here which are not invariant on the sign change of E. And that's the reason why this term vanishes. Next step, assume you have a homogeneous magnetic field in Z direction. Then you would have it here. E equal to minus alpha B palm. And in the original equation for the calculation of the B, you have on the right hand side this term. You know that you can reduce it to U gradient B and E gradient U. B is a homogeneous field in Z direction, so this term is equal to 0. This is a differentiation in Z direction, but U doesn't depend on Z. And so you have 0 on the right-hand side of the equation for B. That is, you have this equal to 0, then alpha parallel must also be equal to 0. So you have a much simpler representation of the electromotive force. Only one term remains, which is represented by E itself, not derivatives. And you see this is just the Z component of B. I think on the next slide I have, yeah. No, I have not. So, I have, if you want to write the relation with a tensorial alpha, the tensor has this simple structure. It has only 2 components, alpha 1, 1 and alpha 2, 2, and all the other elements are 0. If E should depend on Z only, then you can reduce it further and have really this simple relation. E parallel, Z direction is equal to 0, and E perpendicular has only 2 coefficients. Okay. Consider dynamos with this alpha effect. We ignore at the moment also the beta effect. We consider only this anisotropic alpha effect. And first, we assume that everywhere in the infinite space we have this alpha effect. then we can have dynamo solutions of the dynamo equations, and consider the axisymmetric solutions. Axisymmetric with respect to this axis. They have the property that you can always find cylinders which are not intersected by electric currents. And at the beginning, the idea was we cut away all the outer space, and we take this as a dynamo with a dynamo solution, and then it was asked for the smallest. Forgot to introduce this dimensionless measure for the alpha effect, and it was asked what is the minimal value of this, and it came out that just if the radius to height is equal to Z1 over P, you have this minimal value. Z1 is the smallest positive zero of the Bessel function, and it is just 3.83, and so this ratio is just 1.21, and this was taken as a condition for the construction of the dynamo module. It has just this ratio of radius to height. If you have all infinite space, the excitation condition for dynamo mode with this property that you can cut out this cylinder is just 2Z1, 2 times the smallest positive zero of the Bessel function of the order 0, and then other models were investigated. In this case, all infinite space alpha effect. Okay, it looks not very realistic. The next step would be, I have still a conducting medium in the surrounding, but I have no alpha effects there. And what is even more wanted is you have vacuum outside, but you cannot find in a simple way such solutions. Then, for example, a slab was investigated. Yeah, you have here inside this cylinder, and you have either conducting space without alpha effect here and here, or you have vacuum. Psi is a ratio of the external conductivity to the conductivity of the fluid, and you see here results for both. If you look for axisymmetric motions, this C asterisk is 9 or 6, and outer conductivity makes the situation better. You have lower excitation conditions. The same was done with an infinite cylinder, known alpha effect outside, or even free space outside. And so from these considerations was concluded that a dynamo will work if we have this an alpha effect such that the quantity C is, say, an order of 10. One of these values. So far, only axisymmetric solutions were investigated because it is difficult to find other solutions here. No, it is possible, but you don't find basically no solutions where you can cut out a cylinder so that the surface of the cylinder is not penetrated by electric currents. It doesn't exist in the non-axisymmetric. Okay, then a sphere was investigated, And in this case, also non-axisymmetric solutions were studied with m equal 1 and m equal 2. In the axisymmetric case, you have to distinguish between the case where the colloidal field is axisymmetric, so it's this way, and the toroidal field is symmetric. We denote this by AS. Or the opposite, the colloidal field is symmetric, it means the quadrupole field, and the toroidal field is antisymmetric. You have a belt here and the oppositely oriented belt. Yeah. I wasn't successful.
Carry on.
Okay.
Comments. It's unusual combination, right? Of the two symmetries.
Yeah, if you think of stars or planets, yes. But if you think of a sphere with alpha effect, which doesn't change sign between north and south, so it's just the south is just the normal situation. Thank you, Axel. Also, this alpha effect sphere, which I discussed in the other lectures, have this. It depends on the symmetry of the alpha. Okay. By the way, this eigenvalue which was found here is the same as Arquist found many years ago. These authors are new, and you see that indeed non-axisymmetric fields, or at least the m equal 1 field, is easier to excite than the other field. So if this applies to the cylinder too, then it was expected that the field in the Karlsruhe experiment should be non-axisymmetric with respect to the axis of the cylinder. Okay. Later we studied indeed cylinders, but we used a spherical code, and we embedded the cylinder in the sphere, and we made the conductivity here and here and here small. This is psi is the ratio of the outer conductivity here to the inner conductivity, and you see, for example, 1 to 1000 was considered here. Different models were studied with R over H equal to 1, or corresponds better to the Karlsruhe dynamo model equal to 1.21. Yeah, and you see here again, also in the cylinder, always the m equals 0 solutions have the lowest threshold. You can excite them most easily in comparison with these other solutions.
M equals 1. M equals. You said M equals 0.
M equals 0. What?
You said M equals 0. It's M equals 1.
M equals 0. Yeah.
No, 1. Yeah, 1.
M equal. Sorry. M equal 1. Okay. About the geometry of these fields. This is again the axisymmetric field, AS type. You have the toroidal field, and you have here the isolines of the toroidal field. Ignore this, I have a better picture. This is a picture of the M equal 1 field. You see that the field vectors in the middle points here in this direction, at the cover in this direction, at the bottom in this direction. Here are representations, for example, in the XZ plane. It looks like the field of a dipole lying or pointing from the right to the left. It is a YZ plane, and then this is again this dipole which I mentioned, and the field is around it. Or if you look in the mid-plane here, you'll see, it looks again like a dipole field, but it changes with Z, or here is another representation. This is the ER component at the curved surface with a special radius. These are the dephi components at the same surface. This is again, if you look from above on the mid-plane. And here it is the Z component in the mid-plane. The two colors correspond to coming up and going down. It is just a field which goes this way. Okay, this is the field we had to expect in the Karlsruhe time. Okay, I have made so far only statements about alpha, but we don't know how alpha is connected with the properties of the flow, with the intensity of the flow. We have to calculate alpha now in its dependence on the velocities or the flow rates or the Reynolds number. Okay, we do it first in the second order correlation approximation. That means we ignore this term. This is just what defines the second order correlation approximation. And we take the real Roberts, or the considered example of the Roberts flow. Then it is again a simple exercise to carry out these calculations, and you find that alpha is in this way connected with the constants I had in the representation of the flow. Alpha perpendicular is are the amplitudes in the xy plane, and alpha parallel is the amplitude in z direction. Or I can write it also this way with Reynolds numbers, or I can take the flow rates. So consider first V parallel is the flow in z direction, and of course the flow rate in cubic meters per time is a squared, the cross section, times U parallel. And here I consider the flow so yeah, this is a spin generator, this is the axis, and this is the pitch. That is a half, and I consider the flow through this surface. Characterizes the circulation of the flow. I define the flow rate in this way, and then I can express the alpha effect in this way by the flow rates. Okay, so far second order correlation approximation. It is of course not sufficient here. And we proceeded to higher and higher approximations, and I was proud that we could go to infinite order, and so I should before say the difference compared to the second order correlation approximation is that you have only a function of Rm perpendicular or equivalent quantities which you have to multiply with the original, with the so-called results. And we determined this phi going to higher and higher correlations, and we could write down an equation for this phi. This form, say, coefficient are magnetic Reynolds number perpendicular to n equals 0 to infinity, with Cn equal 1 and C0 equal 1 and Cn simple recursion. Okay, we tried to calculate this function, and we discovered that's a convergence of this series ends at RM perpendicular about 3.5. Very surprising. You couldn't see any physical reason for this. And there is no physical reason, but if you consider this series in a complex RM perpendicular plane, which is a pure mathematical thing, this is RM, and this is the imaginary axis, then you see that the function which is represented in this way has singularities here and here. And this is the reason that the convergence ends here. Of course, you can proceed by analytic continuation. You can go from here, here, and so on. But you lose soon all accuracy. And so it is not a practical way to calculate this function. We then went back to this, to this equation, and we subjected B also to a Fourier representation with sin x, or sin or cosine x, and sin or cosine y, and we wrote down an ordinary system of differential equations for the coefficients, and we integrated this this system, looked for steady solutions, and from these solutions then we calculated wrong direction. Yeah, we calculated this function phi. So it is no approximation in the sense of second order correlation approximation is the exact solution. Numerically found exact solution.
So regarding Krauss's convergence proof, if that method didn't work, that is not in conflict with this original idea?
I think there's no contradiction to the general convergence proof, because you can basically proceed to very high values, but it is no practical way. You lose all the accuracy. But it is something what could also happen with Jean-François' procedures. You explain that you do the same. So you must be aware that with such crazy things happen there. Yes?
It's a funny thing, because those convergence problem arise, but if you realize them in terms of ratio of linears, it seems to be always the convergence. And it's a trick that is used in many fields of theory. In field theory, people use that a lot, and it's not really known why, but it works beautifully.
Obviously, there's no physical reason. Mathematical reason which lies in the complex plane. Okay. What we found is this. The question is why it decays. The reason is simply the reason is simply the flux expulsion. With this decay, and here this is what happens in this region of the flow pattern. If you have originally at Rm perpendicular equal to 0 in a homogeneous field, then you have later this situation, and the flux is expelled just from the regions which are of interest for the alpha effect. Okay. So, this is the plane of the flow rates, central channel, emitter channel, and this is a measure for the alpha effect. And you will see how the result looks like. More interesting is to look at this representation. Here are isolines of this normalized alpha C in the DC VH plane. And if, for example, the dynamo, the marginal dynamo number is 9, I think you cannot see the numbers here. That's why I said this is 9. Then it would mean that everywhere below this line is no dynamo, and you have growing solutions above this line. Okay, so that has been done for the spin generator flow. Here the result is a little bit more complex, second order correlation approximation. You have V parallel, that means Z component, U parallel, a Z component of U in the central channel and in the helical channel. Also outside this flow. And that's why the relations look a bit more complex. Otherwise, at least in the second order correlation approximation, it is the same exercise. And here again the general result, independent of the second order correlation approximation, with two functions, phi c, phi h, phi c, phi h, and these two functions has been calculated numerically. It was a paper together with Axel, only in, I think, 2003. Okay. This, and here again isolines of C, and again here I marked plus the isoline with C equal to 9, and again the comment, you have no dynamo below this line, and you have growing dynamo solutions above this line. This is one of the first experimental results. Here are our lines, C equal 8, C equal 9, and this is experimentally determined curves. You see that the theory was, say, C equal 9 was not so bad. And I think somebody else should press the buttons here and make all these mistakes. Okay, here is another experimental result. What is interesting in this representation are you have here the flow rates. It is always order of 100 cubic meters per hour. And you have here the corresponding Reynolds numbers for the flows inside the spin generators. You see they are below 5. It is around 2. It is around 3 or so. That is, there is no Ponomarenko dynamo or Riga dynamo in each separate spin generators. But the dynamo in Karlsruhe is a collective effect of these spin generators. The interplay between these spin generators. Each single spin generator could be a Riga dynamo, but at higher magnetic renaissance. Yeah. This is another measurement, sample measurements. Here the flow through the central channels is fixed, and the flow through the helical channels is varied, and the squares are experimental results. The curve is in the sense a theoretical result. You see this, what we call an imperfect bifurcation. If you start here, you have no dynamo. It is not quite clear where the onset of the dynamo is, and later you have obviously a dynamo. Jean-François explained us that you can all understand, nearly all in dynamo experiments with a Bullard disk dynamo, and I have here a few pictures with this type of dynamo. You explained it. Consider this electrical circuit here, closed this way. The inductivity or the resistance of this circuit, phi times rotation velocity is the time derivative of the flux through here, and you can write, or the electrical engineer will write down Kirchhoff's law, and would find that the current, so also the magnetic field, follows this simple law. And okay, I need not explain it in more detail. Here we added, and you did similar thing, the energy balance. So this is a momentum of inertia, and this is then with a factor and a half the energy stored in the rotation of the disk. This is the energy stored in the magnetic field, and the time derivatives of them are equal to the torque and dissipative terms. This is obviously the Ohm's losses, and this is a friction term. I wrote it here in this way. Rotational energy divided by a certain time constant. And if you say you have at first no current and omega is steady, then you find that the angular velocity is just given by the torque and time tau and the inertial moment. And you see here what happens. You have first for rotation only the trivial solution, and it is stable. And later, if the angular moment, or if the torque exceeds a certain point, you have these two branches of stable solutions. And the trivial solution is no longer stable. And now, next step, you have usually in the laboratory external magnetic fields, the Earth's magnetic field, for example. And what happens in this case, I added here a flux which is not generated by the current. It is, for example, the Earth's magnetic field, slave field in the room where the experiment is made. And what happens then? Just this, you have an imperfect bifurcation, and you have one branch, continuous branch, and you have another branch which is separated from this, and here is the unstable trivial solution. And just this was observed. This resulted from a rough theory, and we have interpreted the experimental results in this way. Okay. I presented here a very simple mean field theory of the experiment, and a lot of improvements have been done, which are listed here. You have to discuss the boundary effects, the effects at the plane boundaries, at the bottom and the top, and the effects on the curved boundary of the cylinder. So, at this point, we admitted a set dependence of the velocity field, and then you see that more coefficients in the representation of the electromotive force are unequal, can be unequal zero. You get a gamma effect again, which pushes out flow from the cylinder and so on. This was discussed with the result that the excitation condition is a bit it is a bit more difficult to excite the dynamo, but the changes are in the range of percent. All this, so it's a curved boundary. Then we have included so far, what I showed you, only the alpha effect, but there are also the beta effects. Just 3 beta effects. I speak about the effects which are caused by the Roberts-like flow, not about turbulence so far. And again, you make the threshold a bit higher, but all this is in the range of percent. You have, of course, in your spin generators also turbulence. Yeah, sorry?
Just in the framework of Roberts'
Yeah.
flow, if you compute beta, your beta perpendicular
Yeah,
and
yeah.
beta 3 from theory, you get a change of the threshold by percent.
Yeah.
Is that what you say?
Yeah, that's what I wanted to say. And this has been done in second-order correlation approximation, but it is enough for these estimates. And so forth. What is not so easy to... what we also estimated is the real turbulence inside the spin generators. So that means the deviation of the Roberts-like flow from the ideal flow. And again, you can make estimates which give also perhaps less than 1%. This is all not very dramatic changes. Limits of the mean field concept. I mean that we assume, if we write down electromotive force, term with B, term with derivative of B, we assume that the higher derivatives don't play an important role. For this, if you consider this in more detail, you see that the ratio of A, this is the dimension of the spin generator, to the radius of the cylinder is important. It is 0.25. If you compare, say, alpha with, or the alpha term, with a similar term, which goes with the second derivatives of B. You didn't write it down, but you must have this term. Or the beta term, with third order derivatives of B, then the square of this factor is between them. And this again might make mistakes in the order of 10%. Okay. Saturation of the dynamo. It is not so much a mean field thing. The saturation of the dynamo is, I think, Jean-François mentioned it already, is mainly by the fact that the profile of the flow in the channels is flattened. That means we have a piston profile and flattened by the Lorentz force, and then it is harder to, or you need more pressure to move the fluid through this spin generators. Okay. Only a few words. We wrote down the dynamo, its equations for B average, split it into colloidal and toroidal field with alpha depending on the flow rates, on the two flow rates, so the central channel and the other channel. And we added equations for these flow rates. First, a term which describes the pumps, so which provides the pressure. Second, a term which describes the resistance in the tubes. And thirdly, a term which describes the influence of the Lorentz force. And from this system, induction equation in two components and two such equations, for example, the curve which I showed you, this imperfect bifurcation results. Okay. Yeah. A last remark. It was often said that the Karlsruhe dynamo works with a known helical flow. So far, it is okay. And it was then said, and the helicity is U curl U. Remember that I explained to you when we considered the alpha effect, not the anisotropic alpha effect in my lectures before, but I showed you that in the low conductivity limit. And low conductivity limit means here simply that the flow is independent of time, it's a steady flow. That alpha can be represented in this way, and I showed you that you can write, instead of this integral, just this expression where psi is the vector potential of U. You can represent the alpha under the conditions which apply in the which apply for the low conductivity limit. You can write it in this way. You can make the same derivations for the anisotropic alpha effect as it occurs in the Karlsruhe experiment. The only difference is that you get here a 2 instead of a 3. Alpha effect can be represented as this way. Now, this quantity, which is important for alpha perpendicular, can be unequal 0 even if this quantity, U for U, is equal to 0. And that means the dynamo should work also without, or also in the case where U curl U is equal to 0. To explain it a bit more in detail. This is cross-section of the spin generator. here is the central channel, here is the helical channel. In the central channel, we have only a flow in z direction. Consider u here as a constant. In the helical channel, we have no radial in cylindrical coordinates, no radial velocity. We have rotation. U phi is just a rotation. Consider omega u1 as constant. And we have in addition a z component, which I have here related to the phi component in this way. If you put epsilon equal to 0, then you have no component in axial direction in this speed generator. Now calculate this quantity and this quantity. This is a simple exercise. You have u per u different from 0 only in the helical channel. If you take the curl of this, you have the curl is in z direction, and you have a velocity in z direction, and you get just this is a geometrical factor, and you have here the epsilon, this initial epsilon. But the situation is different with this second term. I define psi so that the curl of psi is here. This should or think of a similar equation, magnetic field and current. You know when you have a current in this direction, you have a magnetic field even at places outside the ground, where the ground is 0, you have a magnetic field. So, if you have, for example, in the central channel, a flow in this direction, you have a psi, which is also outside the channel. So, for example, at this place, that's a helical channel, and it makes a u psi there. Or consider a current this way, current. No. H. This is just a situation in a coil. Then you have a magnetic field inside. That means if you have a U here at this place, you have a vector potential also in the central channel. So you have, even in the case when epsilon is equal to 0, a known 0 u dot c on the average. And you should, that means you have null perfect, and you should expect a dynamo. Axel made some calculations just with a spin generator I have shown you. First with values which are realistic for the Karlsruhe construction. That you have an epsilon unequal to 0, you have a helical channel, and here two flow rates are chosen with which the dynamo would work. It's just in the marginal state. And we took also this A divided by the wavelength of the magnetic field in that direction equal to 0.9. This corresponds also to the Karlsruhe situation. And then we put it epsilon equal to 0. That means we have in a spin generator only this axial flow, and it is surrounded by a rotation. No set velocity in this helical channel. And we found that we have also dynamo. In order to avoid criticism in the sense, yeah, that is a numerical effect, in the Karlsruhe situation, there is not this space between the central and the helical channel. And the second line was with parameters where this and this boundary coincide. And there could be the criticism, yeah, your numerics is not clean, and there is a helicity in the sense of U curl U just at this border. Then we separated, or made a clear separation. Make a clear separation between them.
Alright.
Yeah.
Is the problem you consider has magnetic diffusivity?
Yeah, of course.
Okay.
Of course.
In which with respect to the size that you are showing, what is the diffusion length? The skin depth penetration of the magnetic field with respect to the three sizes you show.
I have no number, but I don't think that it is relevant here. Let me first finish, and I will then.
And what do you mean by diffusion length?
I think if the magnetic field leaks in between those regions that you define, then it's irrelevant whether exactly a curl U is parallel to U exactly at the point where you consider it. What's important is the action it has on the magnetic field. So if the magnetic field leaks over the whole thing, the argument of trying to separate a curl U with U is just trying to have a large magnetic field make the very small fine difference of what exactly is the structure. And of course you get it done.
But if you want to define a length, that you must have a given time.
Yes.
Well, there is. There's
And
rate,
we consider here, but in this numerical experiment we consider steady situation.
okay, but you have V equal, you have a velocity, right?
I have a velocity.
So you have a velocity and the length, that makes a time. You input that time into the calculation of the diffusion depth, and how large is that? Or not? You just say, I guess what I'm asking is, with respect to how curved can you get a field line, is the distribution of U and phi a small scale distinction or a large scale distinction? Because it is obvious that if I have one flow spinning up here and one flow going there at the other side of the room, then I will not get the floating process. But if they're close enough, I would assume within the diffusion length, of course, they will be interacting and giving a down.
Perhaps let me
Okay.
let me say the following. In the second example, we had a clear separation of 0.2 between the two channels. Conducting medium in between, but at rest. And you have the same effect. The excitation condition is, or the excitation threshold is a little bit higher, but not, the dynamo doesn't come impossible. So, you see what I have written here. You know the paper by Gilbert and others. Helicity is unnecessary for alpha effect dynamos, but it helps, and we should say here, in the case of the Roberts dynamo, the helicity understood as U curl U is not necessary for this dynamo, but as you see here, it helps a bit. So this with helicity and this is without helicity. I don't misunderstand me. I don't say that the Karlsruhe dynamo would also work if you have no helicity in the global sense. If you take a spin generator and consider a plane which contains the axis of the spin generator, and you reflect the situation, the velocity fields, at this plane, I don't say that the original situation and the reflected situation are the same, and I don't exclude this helicity in this global sense. But U curl U is a very special measure for helicity. It is a local measure for helicity. And even if this measure is equal to 0, you can have a dynamo. That's what I want to say.
That's a typical feature of slow dynamos. I think maybe you should emphasize. Not that somebody
we
thinks
have
that
not investigated this here for
not
other dynamos. But nevertheless, it is an interesting thing. This is often said, yeah, a dynamo you can only have in the case you have U curl U unequal 0. It is an example which shows the opposite. Okay, that's all what I have to say.
Thank you very much. So which year was it actually that you started these calculations? I mean, they were of course entering in the planning phase of this experiment.
Yes.
And so which year were this?
So
which year did you start these calculations?
I think
you have
96 or so. I was invited by the authorities of the Forschungszentrum in Karlsruhe to form, to organize a group of experts which should give a judgment whether it makes sense to do this experiment or not. And in this way, I think it was 96, just before the real construction started. In this way, I came in contact with these people.
But maybe it's correct to say that the design phase was already finished.
The design phase was already finished. So also, for example, this ratio R over H was already fixed. We couldn't change it.
So the design was made on the basis that the solutions are axisymmetric.
Yeah.
And then we learned they are non-axisymmetric, so the design should in fact have been different, but it was not changed. It was too late to do.
Yeah.
That's what I wanted to ask. Do we have any knowledge about what the design would have looked like if the non-axisymmetric solution would have been known from the beginning?
Never really investigated this. We have made the theory for the given construction.
I mean,
That is strange that the original discussion by Busse and so started always under the assumption that the magnetic field is axisymmetric. And then we came with our experience from planetary dynamos, so we knew that anisotropic alpha effect can generate non-axisymmetric fields.
Argus knew that in '67 already.
No, Argus investigated only the axisymmetric solution.
Yes, axisymmetric because this arithmetic is a bit more complicated.
Yeah.
And for this time computer it was not simply.
It delivered the axisymmetric solution. And the other values I have shown are then made in computed in Potsdam.
Could this be not the case?
Sorry?
Could this last picture be not the case? Then the Karlsruhe dynamo could not feel any central flow. In central flow, there are three 3 pumps working,
Yeah,
and 2 pumps are giving this spiralic flow,
yeah,
and third pump is giving central flow.
yeah, yeah.
In the central flow, this U cross rot U is 0,
Yeah.
and because of this, there could not be any change, any dependence from central flow.
Are you assuming here again that U per U of the central flow would be important for the dynamo?
No, there is important thing that this is not a one-point correlation. There is a correlation over the whole volume should be. But if one assumes one-point correlation, then central flow could be without any influence.
Should not contribute to the dynamo. You are right.
Yes, and this is experimental test that you are right.
Because the central part does play a role.
Yes, it really does play a role. Another thing is, which is not explained, that this M equal 1 dipole can be in any direction. With
Yeah.
will stay in any direction.
The direction is in the axisymmetric theory where the device is considered as axisymmetric. This direction is not fixed.
Yes, this direction is not fixed, but on reality, in experiment, it seems fixed.
Because the experiment is not absolutely axisymmetric.
Yes, but nothing is analyzed with this respect.
Yes, there's a paper by Andreas Tierner that puts it on geometric method and drawing on this. It's the 54. Is it 54?
52.
52. Is the 52. So if you draw a circle and you're going to put 52 of them, all right? You just stack it by hand, all right? And when you finish doing this, there's a preferred direction.
No, this 52 also conserves 90-degree symmetry.
That's right. But only
yes,
90
but
degrees.
then it can have,
And
it cannot be in any direction. It can be in only 2 directions when you finish doing this.
No. As in any crystal formed with such symmetry, this all effects can be directed in any direction. Why not?
Because if you...
All
this
linear
is,
effects are directed.
it is not a crystal. It's a crystal like this.
But nevertheless, 90 degrees.
Yes, there's 2. You're correct. This only, and once you finish doing this, there's only 2 possibilities.
Yes.
And the experiment chooses one. And then at which point Tierner's paper says that it's because of the field configuration.
But any field in any direction, dipole in any direction, are superposition of 2 dipoles in orthogonal direction with different.
Yes, but if they don't have the
Scales
same growth rate,
and
one will be preferred with respect to the other. And what Karlsruhe has shown is that it was not possible to push the pump enough so that eventually 2 modes would be generated together and interact. What I was telling you before is that if you have an magnetic field line, and if you push here and you turn here, okay, and if the skin penetration is such that you can only change the line slowly like this, it will do. That's all I'm saying. Right? You could have one flow here, the one going up, and one flow going round into these things. And
What I said here is not a question of the geometry of the magnetic field, only of the...
Yeah, but it acts on the magnetic field.
I don't think so. It's relevant.
Yeah, I think it is correct because the non-locality in the expression of the form u times curl u, where the u is at one place and curl u is at another place. It comes not naturally into the derivation of the alpha effect if there is from the beginning a diffusion operator.
Yes.
And
Yes,
but if the diffusion operator is not there, then this correlation is local.
Yes, if diffusion is exactly zero, it's like in Riga, you don't get a Riga dynamo with a zero diffusion. If you think it's just perfect,
What
no,
means the zero diffusion?
lambda going to infinity, mu going to infinity, mu sigma going to infinity.
And then
No.
then you would expect that only the local correlation
sigma.
plays a role. If the diffusivity is zero, but if it is not zero, then the non-local correlation does it.
It's
What
the
you
other
said.
version of the same argument.
What you said.
I agree with you.
But sigma is not infinite.
I know.
So
That's why it works. But that alpha effect in that version relies particularly on the fact that there is a diffusion.
Yeah, but in the device we have both. We have the local and the non-local.
Absolutely.
It would even work without.
No, what I'm saying is I like that argument very much because it makes a point from the theoretical point of view. But but one has to keep in mind that it's a theoretical argument because in reality the diffusion and the non-locality will make it such that these things are not, because the atoms need to align, their separation is not the relevant argument.
Yeah. But what I wanted to say is the statement
Oh, yes,
that
that
is
statement
important
is
for the
absolutely
dynamo
correct.
is not generally correct.
No, it has to be smoothened by the order of the correlation length of the system.
Any other questions? These experiments, of course, are normally named by the place names, Karlsruhe, Riga, Kadarash. And when you actually submit it to a journal, guess what happens? You submit the paper to a physical review and they say you can't call it as this Karlsruhe experiment, the Karlsruhe experiment.
Who said that?
Because Karlsruhe is not in the US.
The physical review.
If we would name it after persons, we had two piloted experiments. Karlsruhe and Riga.
Who said you cannot
The physical review.
But
And the argument is, yeah, they send us a PDF. You remember that, Carl? Thanks. Well, they send us a PDF file which somehow explained it. The experiments shouldn't have a name or something like this.
should not have been.
So
No,
how
we
is it supposed to call them in Hacken?
We called it then a two-scale
Yes.
dynamo
we
experiment.
called it.
Michelson experiment.
We actually called it a homogeneous, a two-scale homogeneous dynamo
Yeah,
experiment.
two-scale.
And now nobody knows which one that is.
Yeah, so it's a Michelson, what do we call it?
You didn't have this experience so far, yeah? But
No, we
but-
publish consistently papers with BTS experiments because that's what it is.
I mean, it's a place name rather than a.
But what about Hubble telescope and such things?
Yeah, I mean, I don't know. I'm not sure whether it applies to persons. Maybe it indeed does also apply to persons.
An orbiting telescope.
Place names.
What?
Not
Place
persons.
names, yes.
Place names, not a person.
Maybe so. I mean, you can't do anything, right? In the end. I mean, the paper was already accepted. You couldn't withdraw. What?
Call it experiment in Karlsruhe, and there must be no objection. It's not Karlsruhe experiment. It's an experiment in Karlsruhe. And that's it.
Yeah, maybe he should
So
have
how
asked
do you
you.
call the interpretation of quantum mechanics to solve
The Copenhagen experiment interpretation, you mean, right? So what will be the next successful dynamo experiment then?
Must be something more American, right?
Yeah, in 2000 we had the impression that there are several experiments under preparation in Madison, in New Mexico, in Maryland, in Perm, in Colorado at this time, and it is quite remarkable that only one since this time was successful, although nobody understands why it is so.
I'll try to make a good argument that I understand. I see there's still some work. There's no reason why the current dynamo should not generate. Seriously, based on everything.
They have technical problems, I think.
Yeah, they have technical setbacks, but on what is involved in trying to build it, I can see why it should not self-generate when it started. There's no objection to that. The people in Madison are basically at the same level we are. So I think we're stuck for the moment in a domain where we need the Taylor impellers to get it done and we can do it. And then later on, as a bet on a large experiment, this only will be the largest everyone's seen. It's 26 tons of sodium. But the flow that is produced from that, as I understand, has no previous numerical or analytical analysis that it should be. What?
No, I'm just applying this when we were picking that dig without the previous analysis. What do you mean by that?
It's because it's impossible to simulate. You can do the little, it's like when we were in Cadarache 5 years ago. You can do your little cartoons and try to understand how things would work if they did, alright? But there is no way you can take a Cadarache experiment, put it on a computer and get a result. You can do it on the mean flow. It didn't seem to be so helpful, alright? You can do estimations on the fluctuations. But then when you're taking a sphere, which was going to be 3 meters in diameter at the Ekman number, which is lower than anything in the numerical simulation, and a Reynolds number of 10 to the 7, then you can't simulate it. So it's relying on the fact that those processes we've been talking about are so robust that they will work.
It's a leap of faith.
Hmm?
It's a leap of faith.
Oh, it's an educated guess, can I say it this way? The difference between the two is rather sweet.
Okay. So we have coffee, but that really concludes then the school. And I wish you all, first of all, a successful PhD, if you haven't got one yet. And don't forget to apply for postdoc positions in time. It's important to think about such a thing before you finish your PhD, normally like a year before that. It's important to get the job before you finish the PhD. And yes, and I hope you will have a great career. So, thanks for coming. And thanks to the teachers.
And we thank the organizers
Yeah.
very much.